Yeah, well, okay. Hello, everyone. Thank you very much for joining us today for the AIAA Los Angeles Las Vegas section event. We have a distinguished speaker today and very, very hot topic. So before that, we have a few words to introduce the AIAA Los Angeles Las Vegas section. We apologize, our section chair, Dr. Jeffrey Puchel, Raytheon, he's actually on a trip. Originally, he said he might be able to call in, but it looks like he got too busy. But he want me to relay the best with everyone, especially the speaker. So on his behalf, I'm going to say a few words. So basically, we appreciate the AIAA headquarters. This platform of Zoom is very, very beneficial. So it's provided by our headquarters, really highly appreciated. Okay, so if you get disconnected, please keep trying to reconnect. It should be just temporary. If any issue, the bandwidth, please try to use the dial in if you have any issue. Also, please sign in with your name. You can change it. And if any privacy issues, please try to use dial in. Some defense contractor doesn't want to use the app. Okay. So if any question for the speaker, please type in the Q&A box. The chat room, please try to reserve for communication with the attendees. You can also chat with the speaker, but the question should be in the Q&A. So, okay, just a few words for Southern California. As you know, Southern California is very blessed for the heavily populated aerospace industry and research community. The shuttle was assembled here, and also the Apollo module, capsule, and many things. And we have JPL, the recently very hot, very exciting Mars 2020 Perseverance rover, and the Ingenuity helicopter. And of course, James Webb Space Telescope, defense, electric hybrid aircraft, SpaceX, Virgin Orbit. SLS is kind of designed here as well. And we have the planetary defense, asteroid exploration expert in the area, and a very vibrant student branches. So a few words for AIAA membership. Once you join the AIAA membership, you will be able to enjoy the Engage platform. You can chat with the AIAA members and expert or other members around the world. And we also have the this is AIAA Daily Lunch, so you can get the insider news, very, very helpful, could change your life or even get business. Then we Aerospace America, very, very nice, magazine, a lot of aerospace information, very exciting. And also you got great discount for AIAA conferences. That's a very good incentive for joining AIAA member. And we also have membership program, high school membership. Then we have events to keep everybody connected to each other. The national conferences, it's a very, very high-end, events for the aerospace technology. So we have been doing events like quantum computing in aerospace, new space mini conferences. Then we have Europa Clipper, Mars Airplane, and Virgin Orbit events. And also for keep the Earth clean, we have green aviation, Earth Day celebration. And we also inspire people, encourage people to do a good job. We have the Excellence Award, the Mars Ingenuity helicopter. You can see in this slide, upper left is our section chair, Dr. Jeffrey Puchel. Then the upper right is our speaker that day for the Ingenuity helicopter. Lower left is Miss Mimi Ang. She's the leader for Ingenuity helicopter. Lower right is a representative for the EDL team from the Mars Perseverance. So this is historic because it's just like the Wright brothers in 1903. So this is first flight in power fly in another celestial body. So this is really the month of Mars. We are very excited to welcome Professor Bruce Jakosky. He's for today's presentation. He's NASA Maven's principal investigator. He's also a professor, geological science, associate director for Science Laboratory of Atmospheric and Space Physics of University of Colorado. He's received his PhD in planetary science and geophysics from Caltech in 1982. His research interests are in the geology of planetary surfaces, the evolution of the Martian atmosphere and the climate, the potential for life on Mars and elsewhere, and the philosophical and the societal issues in astrobiology. He is the principal investigator for the Maven mission to Mars that has been orbiting Mars since fall of 2014. He has published more than 300 papers in the preferred scientific literature and has authored or co-authored a number of books, including The Search of Life on Other Planets. And the other book, Science, Society, and the Search for Life in the Universe. So let's welcome Professor Jakosky for today's wonderful presentation. Thank you so much.
Thank you, Ken, for inviting me to be here today. It's really a pleasure to be able to talk to this group. I am now sharing my screen, and please let me know if you're not seeing my cover chart in slideshow mode. If I listen to my wife, I only know how to talk about 2 different topics. And since ski season is over, I'm going to talk today about Mars. Mars is an exciting planet. There's a lot going on with 4 new spacecraft, 5 new spacecraft arriving at Mars, if you count the rovers and the helicopter, just within the last few months. And what I want to do is talk about the atmosphere and climate, but really it's a broader talk than that, because those tie to the question of possible life on Mars, and more broadly, what the future of humans and the climate might be on Mars. So I want to start with the comment that Mars always seems to be very visible in the public eye. When I look at the online media, when I look at the newspapers, it seems like every day there are new articles about discoveries at Mars. But again, it's broader than that. We see Mars showing up. If you look at the upper left, it shows up in, I hope you see my pointer here, laser pointer. Mars shows up in the name of music groups and in music activities. In the upper right, that's a scene from The Martian, which was a popular movie a couple of years ago. The lower left, of course, in your own Southern California base, is the activities of SpaceX and Elon Musk. And that thing in the lower right, if you know what it is, I don't have to tell you. And if you don't know, there's no way I can explain it. So I'm not even going to try. But the bottom line is that Mars is a really hot topic. And what I want to do is talk about Mars relative to the Earth, Mars, and say something about why Mars is so exciting, why it's such a hot topic. Mars is the next planet out from the sun after the Earth. It's about half the diameter of the Earth, and it's the closest planet. It has an atmosphere thinner than the Earth's, but nonetheless important in affecting day-to-day weather. The geology of the surface is very reminiscent of what's going on Earth. And in many ways, it's very reminiscent of the Earth. I hope you guys will recognize that Mars is the one on the right and the Earth is the one on the left. I put those labels on it just to make sure I don't make a mistake. You can see some fundamental differences from the Earth. The Earth has an ocean. It has a thicker atmosphere. Mars has a thin atmosphere, only about 0.5% as thick as the Earth's atmosphere. And being farther away from the sun, having a thin atmosphere, it's much colder than the Earth, with temperatures rarely getting up to the melting point of ice or room temperature here on Earth. Despite that, the overarching question for Mars is, did it ever have life? Could there have been life in the past? Could there be life there today? And I want to go through some of the reasons to try to convince you that it's not a stupid question to ask. If we look at the criteria for life based on what we know about the Earth, it's really pretty simple. Access to all of the elements out of which you would build life: carbon, hydrogen, oxygen, nitrogen, and a couple dozen other elements that you find in any rocky environment. Of course, the gas elements are available in the atmosphere with water and CO2. You need a source of energy that can be tapped by living organisms to drive metabolism. On Earth, that source of energy is primarily sunlight, but it's not exclusively sunlight. There are organisms that get their energy from the chemical reactions between water and rock. Given that the rock has all of the elements we would need, the limiting factor then is going to be the availability of water. Water is needed as a medium in which life can exist and to support chemical reactions. What I want to convince you of is that Mars has all of these things. The liquid water is the most difficult one, but I think it's pretty compelling that Mars has had liquid water. And that's going to tie into the question both about life and about the history of the climate. These pictures here are the Allen Hills meteorite, just to underscore the potential for life on Mars. The Allen Hills meteorite is one of the rocks that's been picked up on the Earth that has come from Mars. And in this photomicrograph, electron microphotograph on the right, some of the evidence that was put forward a couple of decades ago for the possible existence of, in this case, fossilized life on Mars. What we found from that experience, though, and from the Viking experience in the 1970s, is that searching for life is extremely difficult. It's not something we're likely to do with a single mission to Mars. So we want to understand the context, whether Mars is habitable, what the history of the climate has been. And these are important questions when we're eventually able to bring back rocks from Mars and look for compelling evidence for life. So I want to start with the present day climate. Mars is too cold and dry for liquid water to be stable at the surface. These are images of the surface taken from two different landers, Viking in the 1970s and Curiosity more recently. We see an environment that has a lot of evidence for wind-blown material, a lot of evidence for geological activity. In the picture in the top from Viking, you see dust that has settled out from the atmosphere on top of a large rock. You see wind-blown material, clear evidence for dust in the atmosphere because of the coloring. What you don't see is any evidence here for liquid water or even water ice, although we have other evidence. We do see evidence for water ice clouds in the Martian atmosphere, shown here, two images from orbit, one image from the surface. Even though there's not a lot of water vapor in the Martian atmosphere, it's enough that when it condenses out, it can form optically thick clouds. The amount of water is such that if you condensed it all onto the surface as liquid, it would be about 1/100th of a millimeter thick. That's not very much compared to the Earth's many, many centimeters, but it's still enough to form clouds and to show that there's water moving around in the environment today. For example, we see water ice in the polar caps. This is an image here of the North Polar Cap on Mars, which is water ice. It has dust mixed in it, and it shows layering at a very fine scale, centimeters to meters to tens of meters, that's indicative of evidence for climate change. So we know that the water has been moving around on Mars. The polar cap is what supplies the water vapor to the atmosphere. One of the other components of the Mars climate today, the weather, is the presence of dust in the atmosphere. And we see dust being kicked up in the form of dust devils. Here we're looking at one in the upper left seen from orbit, and it's thick enough optically that it casts a shadow onto the surface. That's a dust devil standing a kilometer or more high. These are seen from the ground as well. You can see in the lower right a sequence of images taken from one of the rovers showing the one dust devil moving across the surface. These dust devils kick dust up into the atmosphere, but they're not the only thing that does it. We also have localized and regional dust storms. The image on the left is one on Mars, and I've drawn in a line just to mark the outline of it for people that aren't used to looking at some of these images. This is very familiar to us. It's remarkably reminiscent of small-scale dust storms on the Earth. This is one shown in the right-hand image, seen in Arizona. This is a feature called a haboob, a very rapid growing localized dust storm, clearly optically thick in its behavior. At the biggest scale, we see Martian dust storms that are global in extent. This is an image showing before and during a major dust storm on Mars, a global dust storm. And the image has, Mars has the same orientation in each image. So you can see the South Polar Cap, one of the large basins, and you can see the extent to which the dust obscures the surface. When we think about the behavior of climate, we base our understanding on these observations of the climate today. The water cycle, the dust cycle, and I haven't talked about it, but there's a CO2 cycle as well, where the major constituent of the Mars atmosphere will condense out. We want to think about how these are going to behave on long time scales. But when we look at the Martian surface, we see other features that tell us something fundamentally different about the long behavior. And in particular, we see evidence that there's been liquid water on Mars in the past. On the oldest surfaces, we see these branching valley networks, they're called, that look very reminiscent of river runoff channels on the Earth. You see the branching tributaries where small valleys coalesce into larger valleys as you move downhill. These form gradually, by analogy with how they form on the Earth, and are thought to indicate that the earliest features on Mars were carved by liquid water flowing over the surface. That is, either water was much more abundant early in history, or the climate was very different. If you look at the middle epochs on Mars, you see what look like large-scale flood features. This is one where you can see the water-carved features going around obstacles and making these, for example, these streamlined islands behind obstacles. If you look at the scale bar in the upper left, that's 100 kilometers. So this thing is this channel is about 150 to 200 kilometers wide. And that means this thing had as much water flowing through it as the Mississippi River does in flood stage. The source of this water is thought to be within the crust, where it was forced up to the surface and then flowed out over the surface. So we have evidence for a different climate early in history, for catastrophic flooding in the middle eras. And at the surface, we also see features at a very small scale indicative of liquid water. These are what were called blueberries that were observed from the Opportunity rover at the surface. They look blue, a little bit blue in this image, but they're not really blue. This is a stretched, enhanced image. I would call them less red berries, but that doesn't have quite the same style as calling them blueberries. These are concretions formed by water flowing through rock, dissolving minerals in one place and precipitating them in another. They've been exposed at the surface by erosion. These nodules, these concretions are primarily hematite, and that is a more resistant mineral than the surrounding rock. And so they're left behind as the rock erodes and leaves them at the surface. And then finally, there are minerals that we can map from orbit that require liquid water to form. Essentially, all of these colored dots represent places where minerals have been identified using spectroscopy from orbit, and each one requires the presence of liquid water to form. Now, these appear to have formed only on the ancient surfaces, so we see evidence that Mars has had liquid water early in its history, and today we have the cold, dry planet that we see by looking at the present-day surface and atmosphere. In addition, the Curiosity rover, which has been on Mars for, about 8 or 9 years now, has been exploring Gale Crater. This is Gale Crater. You can see the crater rim here, central peak here, and then these deposits which have been interpreted as sedimentary deposits. This crater was chosen as the landing site because it's thought to have held a standing lake at one time. You can see here where the water flowed into the lake, over here where the water flowed out. And because there was water standing for long periods of time, we thought this might be a particularly interesting place to explore. And in fact, with the rover team has identified mudstones, sandstones, and conglomerate, all of which form in the presence of liquid water. Here we see sandstone that has been exposed by erosion of the surrounding terrain. And here we see mudstone. You can see the layers that have formed, and you can see that these layers are not all parallel. They have shape to them, and they have cross bedding. These appear to have formed in shallow bodies of water where sediments settle out, driven by the currents within the water. So this is a place that the appearance, the composition is measured by elemental abundances, suggests that there's been long-standing liquid water and that this was a very habitable environment, habitable by microbes, of course. If we think about what does it take to make a warmer atmosphere early in history, the easiest answer is a greenhouse atmosphere, a gas that will trap the heat from the sun and warm up the planet. This purple line at the top shows how much gas you need to add in order to warm up the planet. Over here at the left, that's the average temperature today. As you add CO2 and go to 100 millibars all the way up to a couple of bars, you get to temperatures at and above the freezing temperature. The Earth's atmosphere is right at about 1 bar of pressure. So if you imagine this much gas in the Mars atmosphere as CO2, you could warm up the planet. Early in history, though, the sun was dimmer and the CO2 greenhouse warming would not have been as effective. And during the earliest epochs, you'd have to add something else as a greenhouse gas. I'm focusing on this right now because when we talk about the future climate on Mars, I want you to think of what sort of atmosphere we might imagine creating and warming up the planet. So one of the questions that we have is, where did all that CO2 from the early atmosphere go? If we look at it, we needed a lot of CO2 in order to raise the temperature. Where did the CO2 go? Where did the water go? And can we get it back? There are two possibilities for both of these. They can go up to the top of the atmosphere, shown on the right, and be stripped away to space by the sun and by the solar wind, or they can go down and into the surface and form minerals. This is an example from the same Allen Hills meteorite that I showed earlier, showing carbon-bearing minerals within void spaces, previously void spaces, in the meteorite, that tells us that certainly some gas did go down into the crust. The evidence for hydrated minerals shows us that some water went down into the crust. And observations from spacecraft show us that gas is being stripped away from the atmosphere today. That brings us to Maven. As Ken mentioned in his introduction, I'm the head of the Maven project, and we've been looking at how gas is stripped away to space today in order to understand how much gas might have been stripped away throughout history. What we've seen is direct observations of the carbon, oxygen, and hydrogen on their way to being lost to space. This shows them in an extended corona of gas surrounding the planet. That red circle is where the planet would be if we could see it at this wavelength. The hydrogen on the right goes out as far as we observe to well beyond 10 or 12 planetary radii away from the surface. Oxygen is heavier, it's more tightly bound. Carbon is tightly bound. All of these, though, are in the process of escaping. We also were able to look at the loss of ions, in this case, oxygen ions. The arrows show the direction in which the gas is moving. The colors show the abundance. And by looking at graphs like this, we're able to understand what processes are responsible for stripping the gas away. And if we understand the processes, we can extrapolate back in time. This graph shows an average of about 1 year of behavior. However, it's not the average that may be important. It's the response to storm events from the sun. And this shows the solar event from the largest event we've seen so far in September of 2017. On the left is observations from the stereo spacecraft showing an ejection, what's called a coronal mass ejection, material being ejected from the sun into space. On the right is observations from the Earth showing it appears to be going in the other directions, but as you can see, one spacecraft on the left, Earth on the right, the sun in the middle. We have different views. This is a prediction of what that ejection would look like by the time it gets out to Mars. And this is one of the largest events of the past half decade or so. It was large enough that it hit both Mars on the left. It also hit Earth on the right, and they were in opposite directions as seen from the sun. When that event hit Mars, it triggered a global scale aurora. And this just shows you how big an event it was. On the left is a series of observations of Mars before the event hit at the wavelength where we would see aurora, and you can't see anything. You can't even see the edge of the planet here. And on the right is at the peak of the aurora, and Mars just lit up like a light bulb. This is the biggest aurora we've seen to date, and it's global in extent. What's significant is not the aurora, although that's really cool to see. It's the fact that at the same time, triggered by the same energetic particles that bring you the aurora, we saw the ejection of additional gas to space. And the loss during these solar events may dominate the behavior. The bottom line is when we look at the loss to space that has been occurring over the last half dozen years that Maven has been in orbit, we see the evidence that the stripping of the atmosphere to space may have been it was a major process in changing the atmosphere through time. Moving on, we have the ability to explore some of these places in more detail, and I'm going to come back to the loss to space. These are some of the most cool images I've seen from the spacecraft era, looking with cameras during the entry, descent, and landing of the Perseverance rover, looking up at the parachute, looking down at the heat shield as it dropped away, looking at the sky crane as it lowered the rover to the surface, and looking at the rover as it was being lowered to the surface. When it landed and started taking pictures, it doesn't look like it's a water carved surface. We're exploring the evolution of water and the behavior of water. And in this image, I don't see much that I can ascribe to water. It looks like a lot of the other places on Mars, dirt and dust and some rocks. Some of the rocks appear to have been rounded, and maybe I can argue that that's evidence for erosion by water. Some of them, like this one, have sharp edges and may be carved by the wind. However, it's not a random place that we picked. Perseverance landed inside of Gale Crater, another impact crater. And here you can see the rim over here. This crater is about 40 or 50 kilometers in diameter. Here's where it landed. And this crater was picked because it also showed evidence for being an ancient lake bed. Here you can see where water was flowing into the crater, over here on the right where it was flowing out. And this square is going to be close up in the next image. So take a look at those features. These are the same things. And what you see is where the water flowed into the crater and deposited its load of sediment, it did so creating a delta. And this is very typical of the type of feature that you would get when water flows into a standing lake. The water flows down, it drops its load of sediment and creates a delta. This is exactly what you would expect. This is the evidence that is compelling that this was a lake, and we landed very near to it with the Perseverance rover. The rover is going to explore this in detail, but what makes it exciting to me is that it's going to collect samples on the surface, and those samples are going to be returned to the Earth. Once we bring them back to Earth to study, we'll be able to look for evidence for life in them. We're also going to look at the detailed chemistry of the minerals, of the rocks, but the excitement to me is to have those rocks in the lab here on Earth and to see if they show any evidence for life. Perseverance wasn't the only spacecraft that arrived at Mars. There were 3 that arrived all within a span of about 2 weeks. The timing is driven by the alignment of the planets and when it's easiest to get to Mars. The second one I'll talk about, but the first one that actually arrived there was the HOPE Emirates Mars mission launched by the United Arab Emirates. This one actually is a collaboration with my institution at the University of Colorado. So we played a significant role in developing the spacecraft and the science instruments. Give you a sense of the scale, this spacecraft, this is an artist's rendition, of course. The antenna is about 1.5 meters across, so just about 5 feet. Give you a sense of the size of this. To me, that classifies it as a small spacecraft in terms of both size and cost. The goal of the Emirates Mars mission as an orbiter is to look at the atmosphere from the bottom to the top. And it's the first one that's going to be looking at all altitudes within the atmosphere. And because of the nature of its orbit, all local times throughout the day. So looking at the coupling between the lower atmosphere, the upper atmosphere, and loss of gas to space. Here's just a sampling of the observations from the 3 science instruments. One is a visible imager. This image was the first one taken from orbit by the spacecraft. You can see the 3 large volcanoes, and it's a little hard to see, but over here is Olympus Mons, right on the terminator there, the largest volcano in the solar system. The upper right shows surface and atmospheric temperatures measured from orbit, and the lower right shows this extended gas corona surrounding the planet. Images here of hydrogen and oxygen. So by looking at the behavior of clouds, both water ice clouds, CO2 clouds, dust clouds seen in the atmosphere, comparing them with temperatures throughout the atmosphere and on the surface, and then the stuff escaping to space, we'll get a better idea of what's happening. The third spacecraft is the one in the news today. It's the Chinese Tianwen-1 mission. Tianwen translates as heavenly questions. It's in the news today because their rover just landed onto the surface yesterday. I have not been able to find an image taken by it yet. I think they have not yet released one, or else I would have put it into this talk. This image in the upper left, I think, is a cool one. They carried with it into space a small CubeSat about this big. They ejected it once they were on their way to Mars, and they used it to take a picture of the spacecraft. So this is their spacecraft en route to Mars. This is what the lander and rover will look like. You can see the lander with a platform. The rover here, you can see the wheels, the body, and folded up on the top are solar panels, a mast to raise a camera to higher altitude. The goal of this mission is to understand the behavior of water and ice to search for life. I hope you're detecting a common theme here in terms of what some of the major questions are for Mars. Let me go into what is coming up over the next decade. The European Space Agency next year is going to launch a rover called the ExoMars Rover, and its goal is to search for organic molecules and evidence for life. Oh, wait, this isn't it. This one was searching for evidence for life on Earth. Here we go. This is it. You can see the similarity. They all have common features. Wheels on the bottom, solar panels. This one has a 2-meter drill that's going to drill down into the subsurface in order to get below the top oxidized layer and look for evidence of organics. In the late 2020s, I already mentioned sample return. This is a joint NASA-ESA effort. We'll bring samples back. Also in the mid to late 2020s is a mission called the Mars Ice Mapper, or MIM. This is going to carry a radar with it in order to map out ground ice near the surface that's been recently discovered and that might be usable usable as a resource for a human mission in the 2030s. And then, of course, current plans have a human mission that might be as early as the 2030s. This is one example of what such a mission might look like. It's one that I particularly like because it's a very straightforward concept. This one is Lockheed Martin's Mars Base Camp concept, or as I refer to the company, Lockheed Martian. They also built the Maven spacecraft. We have the ability to send spacecraft to Mars. It's a question of, do we have the will to do it? And let's get started. If we start today, I think we can have a spacecraft with people there in about 15 years. Elon Musk and SpaceX talks about doing it sooner. There are some issues that still need to be addressed, such as the hazards from radiation, from oxidizing agents and perchlorates in the dust, and so on. And I think until we understand those, it's going to be risky to people. Let me talk now about the future climate on Mars. People have been talking about whether Mars can be terraformed in order to have liquid water stable again at the surface. The idea of terraforming Mars is that let's change the atmosphere to one that will trap the heat, raise the pressure, raise the temperature, allow people to work outside, and allow us to do things at the surface that involve liquid water. And that might be something like growing crops, for example. The most straightforward approach is to add a greenhouse gas to the atmosphere to warm it up. And CO2 is the best option if we want to rely on a gas that might be present on Mars today. Now, there's a lot of interest in terraforming Mars. A lot of it is being driven by Elon Musk from SpaceX. I have a quote from him here. "You need to live in a dome initially, but over time you could terraform Mars to look like Earth and eventually walk around outside without anything on." I presume that he means without a spacesuit on, rather than all of us becoming nudists on Mars, but maybe it's the same thing. Mars is a fixer-upper of a planet, in his view. I want to ask the question, is there enough CO2 on Mars to terraform Mars if we could put it back into the atmosphere? And that's the flip side of the question of where did the CO2 go? If we can identify where it went from that early thick atmosphere, we can talk about whether it's possible to mobilize it and put it back into the atmosphere in sufficient quantities to raise the pressure, raise the temperature. So we can think about the places that we can identify that have CO2. For example, there's CO2 in the polar ice caps. We know it's there. We can identify it as ice. We can watch it condense out seasonally. And I'll come back in a minute to talk about how much CO2 and how easy it is to mobilize. There's also CO2 in the ground, molecule by molecule attached to dirt grains. It's a process we call adsorption. That may be one of the biggest sinks today, and it's the most easily mobilized if we could pick up a sample and heat it. There's CO2 in CO2-bearing minerals, carbonates, that have been identified on the surface. Again, this sink for CO2 may have enough CO2 that if we could release it, it would raise the pressure. And then, of course, there's CO2 that's been lost to space. This ties it back to the earlier discussion about Maven observations of the atmosphere, how much gas has been lost to space through time. This is my attempt to summarize how much CO2 has gone into each of those sinks. We have lost to space that may be the biggest sinks, perhaps having stripped away perhaps in the area of 2 to 3 bars of CO2. Polar ice I've mentioned. Clathrate is another, think of it as another ice. Carbonates, adsorbed gas, and then carbonates deep within the crust that have been identified. They have the largest uncertainty because we don't know if they're present only where we've seen them or if we've seen them, but they're indicative of a global layer. So these are the sinks for Martian CO2. And the question is, can this stuff be mobilized and can we put the CO2 back into the atmosphere? So these first two, you can't do it. Once the CO2 is lost to space, it's gone. The solar wind picks it up and takes it out of the solar system. So even though these may be the biggest sink for CO2, there's no way to get it back. The next two are ice in the polar regions, carbon dioxide ice, and they're the most straightforward. We can easily get it back by heating the polar ice caps and causing it to sublimate, turn into a gas, and go back into the atmosphere. However, there's only at most a few tens of millibars. Remember, we need a bar to raise the temperature up significantly. The amount of CO2 in the ice caps might raise the global temperature by a degree or a couple of degrees if we put it into the atmosphere. That's not very much. These last three may be abundant, but it's very hard to mobilize this gas because it's distributed. The carbonates, for example, you have to heat up. And in order to heat it up, you would have to go and basically strip mine the planet. The deep crust carbonates, you'd have to strip mine it to a depth of 5 or 10 kilometers. And the adsorbed gas is also globally distributed. It's very hard to mobilize. So this question, can Mars be terraformed? Really, to me, it translates into the question of, can Mars be terraformed using today's technology? And I think the answer is no. There might be enough CO2 on Mars that if we could put it into the atmosphere, it would raise the temperature significantly, but most of it is not able to be mobilized. It's globally distributed. You'd have to heat it up. It would require mining. That doesn't mean, though, that terraforming is not possible. For example, people have talked about designer molecules, identifying and manufacturing high efficiency greenhouse gases. think of it as analogous to terrestrial chlorofluorocarbons like Freon that are much more efficient than CO2 as a greenhouse gas. This is doable, and it's doable with the elements that we find on Mars. There's abundant chlorine, carbon, oxygen. So in theory, we could create factories that would manufacture these greenhouse gases on Mars and warm up the planet. I want to remind you, though, that we haven't sent anybody to Mars yet. So thinking about large-scale factories and manufacturing is beyond today's technology. Whether it's 30 years or 100 or 300 years into the future, I can't predict. Once it's beyond about 25 years, it might as well be infinitely far into the future. This is my last chart then, and I just want to remind you that we're moving toward this idea of being able to send people to Mars. We could do it with technology that's available today, and we could do it straightforwardly. It's not cheap, and it just depends on, do we have the will to do it? Scientifically, it would be incredibly exciting. From a societal perspective, it would be as exciting as when Neil Armstrong set foot on the moon. It would be that big a deal. So I think we have to think about what we're doing today with spacecraft exploring Mars. We're about to bring samples back to the Earth at the end of this decade that would let us study them in more detail. The next major step will come from sending people as an exploration, not to create colonies, but to explore, to try to answer some of the questions about the history of climate, whether Mars ever had life, and to understand planets in general and our Earth better, and to understand what the distribution of life might be throughout the universe by looking for a second occurrence of life in our solar system. And I will stop there and thank you for your attention. And I will be glad to answer any questions if there are any. Ken, I'm going to turn to you to moderate the questions.
Okay, yeah, thank you so much. This is a wonderful presentation. So I think we have Dr. William Hale. I think he raised hand. So Dr. Hale, go ahead with your question. If you're speaking there, you're off mute.
I did remember reading a book by Robert Forward. I can't remember the name of it, but it was a long time ago, and you know what a genius he was. But anyway, Robert proposed using a reverse Oberth maneuver to nudge these rocks out of the Oort and put them into Mars. As a matter of fact, yeah, it's a long time to get one there, but reverse Oberth, it's not a lot of energy. And, you know, we are looking at time. And he proposed making big holes, the bottom of which would have probably enough depth to have some atmosphere, but most importantly, he would be bringing in these water-bearing rocks, which, you know, we can make oxygen and make an atmosphere out of. Forward had most of this stuff answered long ago. So that was, do we have any ideas like that?
It's doable, but the amount of gas we would need to bring in is tremendous. For example, if we wanted to add enough CO2 to raise the pressure to a bar, we would have to bring in 1 million comets that were 1 kilometer across that were made entirely of CO2. If you want to bring in water and use the oxygen to make CO2 or to create an oxygen atmosphere, you'd need to bring in 1 million comets and release the water. I think that's beyond our capability today. We could bring in a comet, we could bring in an asteroid, but bringing in enough to make a difference, I think is still in the realm of science fiction.
Well, the other thing too is, you know, when these things hit, they generate a lot of heat, which is what you need. And, you know, that's for free once you get it there. So it may change the climate all by itself.
It may change it for a brief period, but and people have looked at that, trying to understand whether impacts could have been responsible for the early warm climate. And the answer is they might warm up the planet, but the dust settles out, the water condenses out, and it just doesn't stay warm for very long. I think that the scale of impact that you do is worrisome, that you would have to do is worrisome as well. Once you had people on the surface, you can't bring in an impactor anymore. It would cover them with dirt and debris if you brought in something big enough to have a global scale effect. I think that's one that needs a little bit more work, to be honest.
Well, Robert Forward also had something like a soletta, which basically just cooked the surface. And Fogg, you know, talked a lot about some major fluoride chemicals to basically trap the heat. You know, I sent this link of this meeting to Fogg. Maybe he can add something to it if he's watching. He's in Britain, so this should be late evening.
You know, those things are all possible, but right now I'm focused on what's possible with today's technology. And manufacturing fluorine or chlorine-based molecules is something that is feasible decades from now, but it's not something we can do today. You know, we're not going to be able to send a spacecraft the size of the Perseverance rover that's going to be able to manufacture gases to make a big difference in the climate. Perseverance does have an experiment called MOXIE that is manufacturing oxygen. And it's a demo to see if it's feasible to do it. And they've succeeded at it, but that's a device this big that is making trace amounts of oxygen. Scaling that up to other gases, I think, is something for the future.
Well, again, you know, changing the albedo, all this CO2 is worthless, but if you change it into carbon, you're going to have a black looking planet, which is going to heat up real fast. So maybe we have some genetically engineered nano plant things or whatever. Who knows? I'm just speculating, but I don't think it's beyond the realm of possibility considering what they're doing with genetic engineering at this time. Just make a black planet.
I'll just say it's theoretically possible, but it's not possible with today's technology. And that's where I draw the line. Let's move on to a different topic, if we may.
Okay, so next question is Mr. Michael McDonald. So Mr. McDonald, go ahead. Michael, can you hear? Well, if Michael is, Mr. McConnell, can you hear us? I saw you raise hand, but we cannot hear you. Okay, I'll read his question. He said, I really meant to ask how that would impact the loss by GW of the Martian surface air, the addition of some given quantity of water.
Oh, he's put something into the chat now.
Okay.
Yes, the Hellas Basin is an impact basin. It's the largest impactor on Mars, and it dates back to the earliest epochs. It's one of the oldest features on the surface.
Okay, so we'll see if Michael's microphone get back. So we have.
Is that possible? Oh, sorry. Oh, yes, I'm getting through now.
Wait.
Isn't it?
We hear you now.
Thank you, Doctor. Thank you. Well, I try to read this paper about the loss of the molecules to space, and that's just very interesting idea. So I think a great deal of observation, right, is necessary before we try to terraform the planet. I know there's a lot of really good science that's going to come out of this, and so I thought, well, let's look at some of the basics. The Hellas Basin was an impact. I mean, that could have heated things up for a short time. Is there any suggestion that might have been where we get Phobos and Deimos, or are these capture, in your opinion? Are these capture?
The question of whether Phobos and Deimos formed in orbit around Mars, possibly from debris ejected by Hellas or other impacts, or whether they were captured asteroids, is one of the big questions that we don't have the answer to for them. The Japanese are planning a mission to Phobos, and maybe from that we will get evidence. I think it's going to require detailed analysis of the samples in order to understand the composition before we can say anything about their origin. I'm agnostic on this one. I don't have a strong opinion. People that pay attention, some people say there are features on the moons and in the orbit that absolutely cannot be created other than by origin around Mars. And there are people that say that there are other features that cannot be created except by their being captured asteroids. So I think we don't know.
Well, it's not decided, and apparently, I'll bet there's some good science there. But the molecules that are being lost from Mars, are they able to be captured by these two bodies? Or, I mean, I guess it's a good excuse for more science.
It is. There are people that are saying that there are rocks from Mars that have been ejected by impact that can be picked up off the surface of Phobos and Deimos. It's possible that some of the atmospheric gases have been trapped there. That wouldn't be where I would go first to look for them, but if we bring rocks back, we might be finding evidence for Mars in them.
This is so very interesting. Thank you for doing this. And I know I'm going to go back and look over these again because this is a really good, interesting science. That's the way it should be.
Thank you.
Thank you.
All right, thank you. So the next one will be Mr. Bill Kelly. Bill, go ahead.
Hi, Doctor. Very good presentation. Mine's kind of a basic question. The stripping mechanism you have described for the atmosphere, is it? I want to ask the impact of the gravity of the planet. You know, the gravitational attraction. Is that the balance? Is it a stripping motion that overcomes the gravity of the planet? Does that make like a minimum size planet for holding a gravity, for holding an atmosphere? You know, those kind of questions.
I'll give you about a 3-hour answer, but I'll try to condense it into 1 minute.
Sorry.
That's the basic thrust of what Maven was doing. Hydrogen and helium are light enough that they can just escape directly out of the atmosphere. It's called thermal escape from the thermal motion of the atoms at the top of the atmosphere. Oxygen, carbon, nitrogen are too heavy. However, there are photochemical processes that can energize them and cause them to be ejected. They can be ionized and picked up by the magnetic field of the solar wind and pulled away. There's another process where some of these ions that get picked up by the solar wind can be slammed at high velocity back into the atmosphere and knock stuff out. Think of it like the break shot in billiards.
Yeah.
So there are a lot of these non-thermal processes that can strip gas away. The key is being able to ionize. The key to all of these non-thermal processes is being able to ionize the gas at the top of the atmosphere. So that depends on solar extreme ultraviolet photons. And then it depends on the solar wind to be able to strip away some of the ions.
So it's not a basic function of Mars has too little gravity to hold an atmosphere. It's a stripping function as
Yeah.
an impact function versus a gravitational attraction thing.
Now, the next question you should ask is, why did this operate on Mars and why not the Earth? And why not Venus?
Or Mercury, right, or anything.
Yeah, well, Mercury doesn't have much of an atmosphere, but Earth does. I think everybody knows that. And one of the reasons that it doesn't operate on the Earth is Earth has a magnetic field that creates a magnetosphere that causes the solar wind to stand off at a great distance. And that minimizes the interaction and the stripping away. Mars had a magnetic field, but it disappeared early. And that turn off of the magnetic field probably resulted in the turn on of the ability of the solar wind to strip away gas. You look at Venus, Venus doesn't have a magnetic field either, but it has a thick atmosphere. And it may be that the atmosphere on Venus is so thick that even if you remove as much gas as you stripped away from Mars, you wouldn't notice it. By looking at Earth, Venus, and Mars as a set of natural experiments, we can get an idea of what properties control the loss of the atmosphere. And now people are applying this understanding to planets around other stars, where we get a sense of how these same processes might have operated there and whether they might be habitable or have lost their atmospheres.
Thanks for that 3-hour answer.
Have I been talking that long? Man.
You missed lunch and everything.
No, I don't miss lunch.
Okay.
Delay it.
Thanks a lot. Great answer. Thanks a lot.
Okay, next is Randall. I don't know if Randall will speak up, but he posted a question in the Q&A. He said, are there any sources of CO2 several kilometers below the surface?
Well, there are two sources of CO2 like that. One is, I've already mentioned, but I'll mention it again, and that is carbonate minerals that are deeply buried. We think these formed early in history when Mars had liquid water. The water could carry CO2 down to the bottom of the crust, 5 or 10 kilometers down, where it could precipitate out as carbonate minerals. The second source is a more interesting one, and that's continued outgassing of juvenile gas, new gas from volcanism. We think that volcanism is still going on today, today meaning within the last, 500 million years, and that would result in release of new gas into the atmosphere. Based on the amount of volcanism, though, it probably isn't a significant source. We'd have to wait 1 billion years to see a significant increase in the thickness of the atmosphere.
Okay, so the next question is by Mr. Thomas Lagarde. So do you want to go ahead?
Well, I think the question has already been asked. It was about
okay.
crashing asteroids with a lot of water content, maybe to increase the water vapor in the atmosphere. But I think you already answered the question by saying that there are going to be too many of them to increase the amount of water vapor in the atmosphere.
Remember also that we have a lot of water on Mars today. If we took the ice in the polar caps, just to give you a sense of scale, if we could distribute that globally, it would make a layer 10 or 20 meters thick. So we don't lack for water. We would need to heat it up in order to put it into the atmosphere.
Mm-hmm. I see. And you think could use maybe solar mirrors or solar concentrators in orbit to heat up?
It's possible. Let's use Earth as an analogy. Mars is 1.5 times as far away from the sun as the Earth is. That means that sunlight goes down with distance as 1/r². So it's about half as much sunlight as the Earth gets. If we wanted to heat Mars up to Earth-like temperatures, we would need to double the amount of sunlight that is incident on the surface. If you did it with a mirror, it's doable, but you need a mirror as big as Mars in order to catch that much sunlight and direct it onto the surface. Again, I think that's beyond our technical capability today, even if it's theoretically possible.
Thank you.
All right, so the next one is Mr. Mark Henley. So Mark, please go ahead.
Sure, can you hear me?
Yeah.
Okay, great. I wanted, I've written an abstract and kind of would like your comments on it. I'd be happy to send that to you, but let me give you the gist of it. It's an idea that I had 20 years ago or so, and then I found that somebody named Thomas von Flandern had suggested it, and he was kind of alternative thinker. I mean, he believed in the face on Mars and things like that. But the idea is that that the Mars had other moons, lower moons at some point that that did decay all the way to grazing orbit and caused the large chasms to form as they grazed and entered Mars's perhaps somewhat thicker atmosphere at the time, and then scraped away, huge chasms that are probably 10 times as wide and deep as the Grand Canyon, and that this so then the continuation of this would be that that it might have opened up a lot of subterranean water and other trapped gases, and all of the energy that would be involved in slowing that moon down as it ground to a halt or broke up would have heated things up as well, so that you would have this tremendous amount of energy that that got deposited, as well as a rip in the surface. So this is the hypothesis in general. It might explain the chaotic regions that seem to be downstream of each of the chasms, that if there was torrential rain that might cause collapse of an area that has a lot of, perhaps it has, was essentially dirty snowfall that the water, transpired away. But that at depth there would be a lot of water, and then it might also explain the sudden flux of water that seemed to occur out of each of the chasms, or except, well, there's some of them that aren't quite that way, the one to the north, but that it's perhaps like a karst topography where there's a collapse after the subterranean water disappears. Anyway, that's the general hypothesis. The thought is that perhaps the lower moon Phobos was stretched past its elastic limit, so to speak, as it got lower and lower and split into two moons, and then the lower one of those two re-entered and Phobos went up a little bit, and then it perhaps did it again and again. Anyway, that's the general idea. It would have been potentially a source of a whole bunch of water and a change in the atmosphere, atmospheric pressure. And hypothetically, one could do it again. You could take another chunk of Phobos and cause it to re-enter, and then, if that was the mechanism, cause another pulse of atmospheric water and CO2 to be released as a terraforming type of exercise. Anyway, that's the general idea. I'd like your comments, and if you'd like, I'll send you the abstract.
Let me talk about two aspects of what you mentioned. The first is what happens when an asteroid comes in obliquely and hits the surface at grazing incidents. People have done laboratory experiments where they do that. There's a facility at NASA's Ames Research Center. They call it the vertical gun facility, where they can send objects into targets at hypervelocity speeds. Even though it's called vertical gun, they can shoot off axis and come in obliquely. And what they see is it doesn't create a long gash. It creates an impact crater that has very characteristic ejecta blanket. Rather than the ejecta going out in all directions around the crater, it goes out to the sides and creates what looks like a butterfly pattern.
Yeah.
That's seen in
I'm
the
aware.
laboratory here on Earth. And we've identified features like that on the moon that we think are then due to grazing impacts. We've also
on
seen
Mars, yeah.
features like that on Mars, and they may be due to moons that have decayed in and come in obliquely, but they create this characteristic butterfly ejecta rather than a long gash. The second aspect, let me talk about the canyons that you mentioned. It's the Valles Marineris system.
Yep.
And if you look at the western end of the canyon system, it looks like a canyon with steep walls and flat floor. At the eastern end, it grades smoothly into these flood features. The alignment of the canyon, though, is radial to the Tharsis Bulge and lines up exactly with what you would expect from the tectonic stress of having this big Tharsis Bulge where the large volcanoes are sitting on top of the surface. It aligns with, it's part of a larger system of faulting that shows variations that are consistent with the tectonic, their tectonic formation. If you look at the geology of the canyons, again, it's consistent with tectonic formation, even though there is that interplay with water. So I think you need to look at the detailed geology of all of these features in order to get a sense of what might have happened. People have looked at that idea of a large grazing impact carving something, and frankly, it has not been seen to be consistent with the wealth of data that we have.
Yeah, I think that there's another very elongated crater just to the west of Valles Marineris, which runs north and south. So it would not be an equatorial moon that would have created it, but it was, thought to be a grazing impact that did create a long, I would say, it seems like a 10-to-1, length to width ratio in that area. So you probably know the one I'm talking about.
I'd have to go back and look at it.
Okay.
Even though I'm familiar with the geology, when we're talking about the geology, I'm going to claim to be an atmospheric scientist.
Well, sure.
By the way, when we're talking about the atmosphere, I'll claim to be a geologist.
That's okay.
I am a professor in geological sciences, and the way I think of it, by looking at the top of the atmosphere, we're just looking at the thinnest, most tenuous part of the geology.
Well, sure. And then some of the atmosphere is in the rocks now. Let's just see. I guess there's one related question, and that has to do with the timing of all this. Of I think that the consensus of thought now is that the water flowed quite a while ago, a billion years or something like that. What's the rationale for that compared to, something that could have been more recent? Cratering rates on the plains or
right now we try to date the surfaces on Mars by counting how many impact craters are on different types of surface. The longer a surface has been there, the more craters it would accumulate. And then we tie it back to an absolute age by comparison with the moon, trying to understand the differences between the moon and Mars, the impact rate on the moon and Mars. For the moon, we have the luxury of having return samples that let us get absolute ages for some of the surfaces that we see. This puts I'll call it the drying up of Mars. that transition from an early warm, wet planet to a colder and drier planet at around 3.5 to 4 billion years ago.
Yeah.
So very early in the history of the planet. That timing makes it exceedingly difficult to uniquely understand the process responsible for the changes, because a lot of things were happening at that time. The rate of volcanism was decreasing, the rate of impacts was decreasing, the atmosphere was being stripped away by the solar wind. The amount of volcanism, I think I mentioned that, was decreasing. So we see those things all happening at once. There's some evidence for liquid water flowing over the surface throughout history, but that global scale warmer environment was early in history and then came to a stop. There may have been brief periods of a warmer, wetter environment or localized water since then. There are places where we could even look today to find localized liquid water, but not global in extent.
Yeah. So I have a kind of one related question. And this is more related to the global water situation on Mars at some time in the past. In that when I look at Olympus Mons, I see a change in slope that looks in a way similar to the change in slope that you see in the Hawaii volcanics on the Big Island, on the Mauna Loa. So, you know, where you would expect a low slope that goes down to sea level, and then below sea level you have a steeper slope. And I don't know the general thought on this, but were there oceans on Mars that were kilometers deep at some point? That's the question.
That's one of the raging debates. There's some evidence for an ocean seen in features that some people interpret as shorelines.
Yeah.
And I showed at least one picture of the catastrophic flooding, and you've alluded to it as well. That certainly released a lot of water that would have flowed into the northern lowlands. And when it did so, it would have at least briefly ponded up and created a sea, if not an ocean. But the extent of any body of water, the amount of water in it, and the longevity, how long it lasted, are all hot topics of ongoing debate.
Okay, thank you, and thanks for all your work. I used to have your book called Mars out. I think you were editor, perhaps. I had it on a long-term loan, and they kept wanting it back. And but it was good to meet you. Thank you.
Thank you.
Yeah, Professor, you mentioned the volcanic, and Randall has a question about this volcanic. Randall, do you want to speak out, or should I read it for you? All right, he doesn't. Okay, so then, because you also mentioned Elon Musk, I think Elon Musk also mentioned something like this. So do you think it will be possible to stimulate dormant volcanic action with a powerful nuclear device?
No.
I was about to ask this.
I think we don't understand volcanism well enough to know what a trigger might be. And I think the planet, nuclear devices put a lot of energy locally, but compared to global scale volcanism, it's a drop in the bucket. The amount of energy involved in volcanic materials is many, many times higher. So I think that would be like, I'm trying to think of a good analogy. I was going to say it's like using a match to trigger a fire, but that's probably the wrong analogy here. No, I don't think it's possible.
All right, understood. So we have Pratik. Pratik, do you want to go ahead?
Yes, sir. Hello, everyone, and thanks for the talk, Professor, and everyone here who asked questions before me, because most of my questions got answered in that way. Thank you, everyone, for that. and mine is a little novice because I was trying to take notes while everyone was talking and you were giving presentation about it. And I guess most of it got answered, but again, I got lost in taking notes. Professor, you mentioned about the sources and the drain of the carbon gases, right? And then you also talked about different sources from where we can, I mean, the sources, how we can generate things, especially the CO2 gases and all of that. So my question was related to that. What about retention? And a part of it got answered because I was thinking the nuclear, because how to retain it. And you also spoke about creating a magnetic field, and because Mars lost it. And I was thinking if we can go, I mean, or to devices, we can create a similar conditions using and creating a magnetic field so that the retention could happen. So I would want to ask your views about it, excuse me. And I mean, if you could direct me some resources where I would read more about it, that would be wonderful too, because since you have more experience about different things in your slide that appeared. So could you please talk more about the retention process and how can we go about it?
So first I'll say that Jim Green, who is the chief scientist at NASA headquarters, has suggested the idea of putting a spacecraft between Mars and the sun to generate a large magnetic field that would cause the solar wind to go around it and miss Mars, and use that as a way of protecting the Mars atmosphere. I'm not too worried about the need to protect the atmosphere, though, because the loss mechanisms all are driven by the solar extreme ultraviolet radiation. And that radiation was so much greater early in the solar system, early in the history, and it's been declining rapidly. So all the loss that I've talked about, the bulk of it occurred between 3.5 and 4 billion years ago. Loss is still going on today, but it's going on at a rate of a couple of kilograms per second globally. That's enough to remove the entire atmosphere, and I think it's about 75 million years, which means I'm not too worried about it. If we could put gas back in the atmosphere, it would stay for that same time scale, tens of millions of years. I'm just not worried about retention.
Okay, thank you, Professor, for that. I'm sorry, I interrupted someone. Please go ahead.
So you mean you finished your questions? If so, we'll move to the next question. Or you still have more questions to ask?
I had actually, but I lost the thought. Sorry about that. I'll
come back again if you pick it up.
Yes, sir, definitely. Thank you for that.
Okay, so next question is from anonymous attendee. He said, could we drill a well deep enough to get 0.3 bar of oxygen to make a livable space?
That's a problem. That's a lot of oxygen. If you know the amount of gas required to thicken the atmosphere globally is tremendous. It's of order 1,000 grams per square centimeter. And that doesn't sound like much, except that Mars has 10 to the 19 square centimeters. So it's a lot of gas you'd have to put back into the atmosphere. It's relatively easy to build a dome that would retain a thick atmosphere and stay warm. Relative easy in some relative sense. Compared to trying to change the global atmosphere, it's easy to build a dome and keep an atmosphere locally. But I just don't think it's within the realm of plausible to do it on a global scale. What I keep coming back to is is it possible with today's technology? And I think the answer is no. And if you require fundamental new inventions and miracles to create new technology, you can do anything. And we'll have those. Those steadily occur, but I can't tell you if it's going to be 30 or 300 years or what discoveries will allow us to do it.
Okay, great. Before we move to the next question, actually, I have a question, because people are talking about using ISRU, using the Martian atmosphere to make a rocket fuel, make oxygen. So that's another source of loss of the atmosphere. Do you think that if we have a lot of people move there, are going to consume a lot, and is that a concern?
Like I said, the planet is really big. It has 1.4 times 10 to the 19 square centimeters, and the atmosphere today is 15 grams per square centimeter. So that's about 10 to the 21 grams. That's a lot of gas. I don't think we could use it up by making rocket fuel for a few rockets or oxygen to breathe. I'm not worried about the sustainability in that sense. We wouldn't use it up for a long, long time.
Okay, great. So Michael has a question. So Michael, do you want to ask your question, or should I read it for you?
Oh yeah, sure. Let's see if I got it unmuted now. Yeah, you want to talk about? Would you tell us more about this UAE mission? I think if you were involved in it, there might be some very salient points here.
It's the first mission to Mars from the Arab world, and it has to date been a very successful mission. It launched, it's operating, it got into orbit at Mars. It's in its science orbit. The team just finished doing checkout of the instruments and week-long tests of the observing schemes. And I'm looking over at my calendar. In 8 days, we're going to declare the start of the science mission. And at that point, we'll be taking measurements regularly every day for an entire Mars year, and using the types of data that I showed to understand the dynamics of the lower atmosphere, the coupling to the upper atmosphere, and the escape to space. It's that coupling that I think makes the mission exciting, because we've studied the lower atmosphere, we've studied the upper atmosphere, but we're learning that it's the interactions between the two that may be driving the processes. So we're going to be exploring that with the HOPE mission.
Maven Space Science Systems used to put out periodical weather reports. Can you see that type of thing here? Are we going to get Martian weather reports on a daily basis, maybe, or weekly? Or
I will suggest that to the team. We're having ongoing discussions right now about how to release information to the public and how to engage the public. And that might be one way to do it. Since we're looking at both the lower atmosphere and the upper atmosphere, maybe we can even do space weather reports on a daily basis.
This sounds compelling. And I wondered too if there were experiments continued from Maven or maybe related scientific instruments here.
Absolutely. Maven, it's been operating in orbit for 6.5 years. All of the instruments are continuing to operate nominally. The spacecraft operates nominally, and we're getting data back every day. In addition, the Mars Reconnaissance Orbiter is operating and collecting data. The Mars Odyssey spacecraft operates and collects data. Trace Gas Orbiter, which is a collaboration between ESA and Russia, is operating. And the Indian MOM mission, Mars Orbiter mission, is still operating. So I've lost track on my fingers, but that's either 5 or 6 spacecraft that continue to operate in orbit. Oh, and the Chinese, I forgot the Chinese orbiter that went along with their lander. That's operating. So we have a lot of spacecraft still sending data back. On the ground, we have the new Chinese rover, which is just getting started, Perseverance, the helicopter, which is really coming to the end of its mission, and the InSight lander looking at the geophysics of the planet. This is an incredible wealth of information, and collectively, it's overturning our views about how Mars operates. That's what happens when you keep collecting new data and new types of data.
Would you say that the model of the Martian atmosphere is as high resolution, if you will, as our Earth model, or?
No, we don't have the type of global scale measurements at Mars that we have of the Earth that drive the models of dynamics. You know, when I go and look at the TV and see the weather report for tomorrow, that comes out of a computer model that takes all that input from around the globe and then uses that to predict what's going to happen. We have orders of magnitude less data at Mars, so our models are that much less well developed. With the HOPE mission, we're going to have for the first time full coverage geographically and throughout the day, all times of day. So that's going to be a major change in our understanding of how the atmosphere operates. And then the coupling to the upper atmosphere will help us in long-term behavior. So I think we're going to see a lot of new information coming out.
Well, it certainly sounds very interesting. I have to think that they've put up maybe a website or something somewhere, or maybe you're still discussing this type of thing.
If you do a Google search on HOPE Mars mission, it'll turn up the website for the project. It's based out of the UAE. I think it's called something like EmirateSMarsMission.ae or something like that. I can't remember off the top of my head, but it pops up right away in a Google search.
Well, I'll certainly look for that Martian weather report, because I miss those, and that I'd like to see that on the weather, on the news weather, and the Martian weather. I mean, but we're not going to get that except for places like here. So, thanks again, Guy. Thank you.
Thank you.
Yeah, Professor, actually related to this question, are those three missions, when they got launched, or do they coordinate each other, like the UA, the HOPE and the Tianwen? Do they talk to each other to coordinate their mission, or they actually do it separately?
The missions talk to each other to make sure they're not going to conflict with each other. It would really be not a good idea if you launch two and they collide with each other. But other than that, each one has its own set of constraints. They're launching from different places. That gives them different initial velocities. They carry different amounts of fuel in order to get into orbit. The delta V requirements are different. Right now, the missions are coordinating to make sure that they don't hit each other in Mars orbit. There's a collision avoidance process at Mars. That's run out of JPL, but I believe it includes all of the orbiters, including the HOPE mission and the Tianwen Chinese mission. There's also coordination to make sure that the radio frequencies don't overlap, because you wouldn't want to get that type of distraction in your radio frequency, that type of noise from somebody else's.
And also does Maven serve any other function, for example, relay of the data for some?
We have an Electra relay, and we are providing relay data for both insight and curiosity. That frees up MRO to be a relay for Perseverance. Trace Gas Orbiter is also providing relay data. In addition, the Maven team is collecting the available information on space weather and giving a heads up to the other missions when we think there's going to be a solar storm that hits Mars.
Yeah, excellent. Yeah, actually, also about the, actually, it's very exciting you talk about Venus, Earth, and the Mars atmosphere as kind of comparison. We have been having events from Mercury to Pluto, and recently we also have the talk about Venus atmosphere, of course, phosphine, and also Earth climate change by JPL Earth Science Department. And also, have you talked about Mars? And there's a question, with the Earth, in between Venus and Mars, and is there any danger that Earth will be moving into either way, kind of extreme? No, not right now.
No, there's nothing that would apply a force on any of the planets that would be able to move them.
No, and also you mentioned it's probably require a lot of comet or asteroid to put CO2 or water on Mars, but we do have a lot of CO2 on Venus, right? Do you think?
So my dream would be to take all that CO2 from Venus and move it to Mars.
Exactly.
And then we would terraform both planets at once. But if you think about how much CO2 you need to get to Mars, if we could start creating ice cubes out of the Venusian CO2, we'd have to have 1 million kilometer size ice cubes to get very much atmosphere to Mars. In theory, one can imagine ways that might be possible. In practice, it's not possible today, of course. I have stopped hearing anybody. Are you guys still there?
Yes, we're here. Very
Okay.
Good. So I think there is a question from Anonymous. This is regarding to the books. So Professor, could you recommend some books for us, the novice, for young student to read on the subject of Mars climate? And does your public science society and Search for Life in Universe talks about Mars surface climate? Thank you very much.
My book, the book Science Society and the Search for Life in the Universe, was aimed at thinking about the broader societal impacts of searching for life elsewhere and maybe finding it. So that's not a good place to start. It's more of a philosophical discussion. There are good textbooks that talk about these topics. The ones that come to mind are at the college freshman level, either a freshman astronomy textbook, or if you're more interested in life, there are astrobiology textbooks. And any one would be excellent in this area. Right now, no specific one is coming to mind. And at a lower level, I don't have anything in mind at all.
Okay, and there's also a question, do we have a Google Mars so we can study each part of the surface at will?
Yes, and if you do a search on Google Mars, you'll find it. It's put together by the group at Arizona State University.
Ah, I see, very interesting. Yeah. I think that your books is very interesting because you talk about, not only the science, but also the philosophy, and also think about the future, the society. I think that's what people need. It's just not the data. It's something what human need to do in the.
We've seen here one of the things that makes it exciting. We've seen it here today that people are interested in this, and as an example, I don't get out to meet the general public very often. I'll talk to people on airplanes. Well, I used to talk to people on airplanes. Nobody does that anymore. But I remember once I was in Washington and I had a meeting at NASA, and I got into a taxi cab and asked the driver to take me to NASA headquarters. And he started into this long monologue about water on Mars and the possibility of life. And I was thinking, wow, how cool. Even the taxi drivers are interested in this stuff. And it didn't bother me at all that the next sentences out of his mouth dealt with UFOs and alien abductions.
I see.
People are still interested in this. They want to know about life elsewhere. They want to know about climate on other planets because it helps us understand our own existence here. And even asking about aliens and UFOs is a different way of asking the question about, is there life elsewhere, and what does that mean for the nature of our life here on Earth?
Exactly. Actually, we have been trying to also set up some kind of UFO event, but it's professionally, with the recent sighting from the Navy pilots and those things. Just because because your topic is so important and interesting, and people is excited about the helicopter on Mars, but you need atmosphere to fly. Those helicopter, or we have Dr. Dan Raymer, our fellow AIAA, designing the winged human airplane. So this is very critical, and the survival for people settling there. And then you mentioned about maybe if we started now and focus, have a determination, we can do it in 15 years, right? That's what you can say. Recently, I happened to kind of attend an event by astronomers. His name is Martin Rees. He's an astronomer. I think it's for quasar and the black hole. He kind of had more pessimistic. He kind of feel that Elon Musk plan this kind of space settlement would not work, for maybe next 100 years or 150 years. So, but according to what you were saying, is kind of promising. So what is your source of confidence that if we have determination, we can do it in 50 years? And they also mentioned the sustainability is not a problem.
Well, there's a large gradation here. With the first missions that we send with people, it's really easy to create an environment they can live in. You send something the size of a Winnebago trailer, and you have an enclosed environment. That's very straightforward. Anything beyond that, whether we create a dome that we have people live in, that's far into the future. And when I've tried to think about what the future holds, I can make predictions going maybe 25 years and have some hope that they'll happen. Beyond that, you can't tell what's going to happen. So what may have come across as optimistic about creating environments is really a desire to not be pessimistic. I don't want to say that terraforming is impossible because I don't know. What I do know is terraforming Mars with today's technology is not possible. And I can't predict what tomorrow's technology will look like or what might be possible. I can't predict when we might have enough activity at Mars, enough people on Mars, that we could create the manufacturing capability to make greenhouse gases in sufficient abundance. But that, if we wanted to manufacture Freon as an example, maybe not the most efficient gas, we would have to have factories that make it at a rate greater than we made all the Freon on Earth because it's destroyed by sunlight. That's a lot of factories. And I think that pushes it far into the future. And I can't predict what's going to happen 50 years from now.
Yeah. And they also mentioned about the radiation as a potential issue.
That's right. I'm going to need to wrap this up. I've got another meeting coming up on the hour. And
yeah, thank you.
Ready for it.
Yeah, it's really our great pleasure and honor. It's so exciting. So thank you so much. So please stay in touch. We will keep in touch with you, and we should have a great opportunity again with you.
And it's been my pleasure to talk today, and thank you for inviting me. It's just a delight to be able to talk about Mars anytime, any place.
Exactly. Thank you. Thank you, Professor. Thank you so much.
Thank you.
Okay. Thank you. Thank you, everyone. So that's conclude today's AIAA Los Angeles Las Vegas section event. So thank you very much for attending. Look forward to seeing you next time. Appreciate it. Have a good day. Have a good weekend. Bye-bye.